Okay, good afternoon. Let's get started. Um, so a couple of announcements. You should be ready to work on your project now, based on the second report. You have everything you need to prepare your model for the location that you're studying. So the recommendation is for you to get started on that. You can set up your system, use the probability distributions that are part of your report, and also start running some replications and see how the values that you get from the simulation, for example, cycle times, working process, queue length, those statistics that you collected for verification and validation of your system, those are the ones that you're going to be using once you run your simulation to verify, validate that your model is representing the problem that you study in your project. So you can get started with that. If you don't, you also have the project description on Canvas. There's the description of the last report is there. So I encourage you to look at that and come with questions on Wednesday. If you haven't looked at that yet, you can look at that, and then on Wednesday we can have some discussion on that last report for the project. We are also getting towards the last couple of labs. So we're going to have 10 labs this semester. This is going to be lab 9. Next week, we're going to have lab 10. And that will be the last one. So in terms of preparing for the second exam, the second simulation exam, you will have 10 labs to study. And the exam is going to be based on those 10 labs. I'm sorry, 5 labs that we cover after the first exam. So you can start also looking at that if you want to get ready for the second exam, second simulation exam. The date for the exam is also listed on the syllabus. So that's that. And today we're gonna do some new modeling or some important modeling techniques that are commonly used, or that for situations that are common in industry. And we were going to be focusing on how to model failures in machines and equipment, how to represent that in Arena, which is kind of simple, but we're going to go through the details today. And then we're going to work on a model in class, and that will be it for today. So anybody facing issues with Arena? I think I found a solution. I was able to fix my machine. So today, hopefully, my machine is going to be working and performing as expected. I tested it this morning. So the problem comes with the reports that are generated by Arena. Okay, so what I found out was if you have a version of Office, Microsoft Office in your machine, and that Office version is not matching the 64-bit requirement of Arena, for example, if you have a 32-bit Office version and you're using a 64-bit machine and you're using a 64-bit version of Arena, you will face problems. So what I end up doing was I removed all my Office products from my machine. I uninstall also Arena, and then I install Office again, 64 version of Office, and then I install Arena again, and that solved the problem. When you do the installation, if you go to, let me show you something. So I know this is might not be relevant for all of you, but I know some students are still facing problems. So that's why I'm spending some time doing this. If you go to if you download the Arena model, you have this folder called, I'm sorry, yeah. No, why? It's connected. So you have this media image folder, and then there's a folder called install. You go to Arena, you have to use this setup file to install the software, because the setup is going to look at all the requirements for the system to see if the system meets all the requirements that are needed for Arena to work. So again, this is what I did, and it worked. Uninstall Microsoft Office, uninstall Arena, download, in my case, 64-bit version of Office in my machine, install it, and then install Arena, 64-bit version of Arena. You have to make sure that if you want to install the 64-bit version of Arena, that you have the 64-bit version of Office in your computer in order for it to work. Okay, so hopefully that can help you get everything installed. And then there are other things, like for example, if you have these applications like Visio or Project in your machine, those are also Microsoft products. So those also have to be 64-bit. So the requirement must match. Okay, so let's go to the presentation for today. So this is what we're going to be discussing this afternoon. We're going to be looking at failures for our resources. So let's go straight to that. One thing that I got a student this morning asking me about the assignment for today and how to model the model for the Sega machine in today's exercise. You got 40% of the parts going into machine 1, and then 60% of them part type B, I think, going to machine 2, but machine, I'm sorry, 2 second to the second part type, and that part type can be processed by either machine 1 or machine 2. So the way you model that, you represent that into your system is by using these sets. Okay, so you need to define a set in which you have both machines, and then also define an expression in which you have both machines. And then you will call that set for part type 2. Okay, so that's how you represented that for the second part type. Also, there was a question about priority. So let me open Arena. So how to set up a priority in Arena? You can you can specify that for the part types here. So if you want these entities to have priority on this resource, you can set up the priority to high here. So if you didn't do that in the assignment, that's okay, because I don't think I explained that in class, but I'm explaining it right now. So if, for example, in the exercise, part type 1 has priority over machine 1. So for machine 1 or for part type 1, you would put a high priority. So they will have go first in terms of CC machine 1. Yes. Okay, yeah, so I think so the question is, in the exercise, I gave you the description of the processing times, and then I told you that it follows a gamma distribution, but that information that I gave you are not the parameters for the gamma distribution. Okay, so you have to use those parameters to find, you have to use those times to find the parameters for the gamma. I stated that in there. I didn't do it in class, but that's something easy. That's something that you can easily find online, how to do the transformation from processing times to parameters. But I did give you the right probability distribution. So you can do that exercise on your own, how to transform that. That is not part of this class. So that was like an extra comment for you to remember that for gamma, you have to find the right parameters. So you will get the information and you have to find the right parameters. And this will differ in different software packages. So you have to find out what are the parameters that are used in Arena. If, for example, you use Simio, you might see that they use the same parameters, but maybe the order is different. So you have to always look into how the software is integrating those parameters into your probability distributions. So that was the main issue when putting that comment there, that you are aware of the differences between the software and parameters and how those are linked to the information that you get. So that being said, resource sets, you needed to use this in the assignment and the expression as well. Schedules were also used. So that assignment had a lot of things. Schedules, you also needed to specify these rules. And then today we're gonna look into the resource failures. So again, very straightforward, nothing, just making sure that you have the right information and know where to put it. So resource failures, this is under the advanced process. Again, using those modules like spreadsheet format modules. And this allows you to define expressions in terms of multi-dimensional aggregates. For example, if you have multiple employees, have different processing times, you can use those to expressions to store the processing times. You can do the same thing for the failures. So what are the parameters? You have to name the failure because you're going to be linking this to a specific resource. And then you have to specify how the failure occurred. So there's two ways. One is by counting the occurrence of a, for example, the number of users that you have in the machine. And if you are modeling the failure based on the count of usages, for example, this doesn't have to be only a failure. This could be like a setup or preventive maintenance that you want to perform in the machine. So for example, if you want to perform some type of preventive maintenance into the machine, You want to count the number of users that the machine has and then set up the time or use a failure to represent the preventive maintenance being performed to the machine. So again, this failure strategy can be used to model different situations. But the most typical one will be you have a machine that has been working for a long time, no maintenance has been performed, so at some point you know it's going to fail. So you can model that from two perspectives, counting the number of usages. So for example, if you typically see that after using the machine 100 times, there's a failure, you can do that. Or you can do it based on a time interval. So how many hours, how many days, how many months this machine is being used, and then we have a probability distribution associated with the time between arrivals of these failures. And then we program that distribution to model when the next failure is going to occur. So the time by time interval is going to be looking at the uptime. How long is it operational before failure? This could be, again, in terms of seconds, minutes, hours, or days. Uptime in this state only. You can specify if you want to consider time in which the machine is idle as part of the time that you are counting towards the next failure, or if you're just looking at the amount of time in which the machine is in use. You can specify what you want to use to represent the next failure. So uptime in this state only will only consider uptime given a certain resource state. For example, be busy or in use. Downtime, how long is the machine down? So you also have to specify how long is it going to take. So it's not just representing or getting information about when the next failure is going to happen, but also you want to model the downtime for the machine. So how long is it going to take for you to get the machine back to a good status? So mean time to failure, mean time to repair. You remember those two? That's what we are trying to model here. Mean time to failure, how long till the next failure. Mean time to repair, how long until the machine is back to operation. Downtime in units could be also in seconds, minutes, hours, or days. So what are the different situations that we can model using this failure mode? Workers goes on a break. So if you don't know for sure when this is going to happen, you can represent it using these failures. Machine breakdown, machine is scheduled maintenance. Those are also situations. An employee gets sick and leaves work. Those are all other things that can happen. These are all methods in which a resource failure can fail, or a resource can fail, and must think about the problem to determine how to classify a resource schedule, a resource failure. So it depends. Again, you have to understand the problem, whether or not this is important for you to consider as part of the abstraction for your simulation. And if that's the case, then think about how to model that from this perspective. So again, if you know that a worker goes on a break every day at 12 o'clock, you don't have to use a failure. You can use just the schedule and then put the capacity of that resource into 0 from the amount of time that is needed, and then the resource will go back on after that. But if this break happens randomly, you are not sure when this is going to happen, then you can use a failure to model that that behavior, which is uncertain. Okay, and then same thing for the machine breaks down. You don't know what's going to happen, so you're trying to model the mean time to failure, the mean time to repair. So in terms of the statistics, today we're gonna be looking at a variable to to follow the number of, or counting number of units per day. So typically we will use a counter for those, but the counter is limited in terms of, like if you're running a replication for 10 days and you use the counter to count the number of units being processed, it's just going to give you the number at the end of the 10 days. But if we want to compute the number of units completed per day and you're running this for 10 days, we need a variable to keep track on the number of units being completed every day and then do an average. So I'll show you how to do that. So what else? Okay, so let's look at the example. So today we're going to be using the same model that we built last time. So hopefully you have access to that model in your computer. So if we remember, this model has two machines, 50-50 for the parts arriving into the system. And these entities are arriving following an exponential distribution with a mean of 5. We have 3 shifts for 2 machines. Machine 1 is working all day. Machine 2 is off. It's not up between 4 p.m. and 12 a.m. Oh, yeah, that's correct. So that's right. So this, let me fix that. It'd be 2 and 3, right? Thank you. Yeah, we changed that because we had an issue with the number of units generated exceeding the 150 limit for the educational version. So thank you for the reminder. So these are the probability distributions. And then we have routine maintenance is performed on both machines at 5 p.m. and then maintenance takes 30 minutes. So we represented that all using our schedules for the machines. And then we want today to have we want to compute the mean number of parts per day. Okay, so we're going to do that for every day. And we're going to run this for 10 days. I'm sorry, for 10 replications. Each replication will last for 10 days. And then we're going to use the 2-day warm-up period. Okay, so you'll see what that means in a minute. And then the other thing that we want to do is to look at the time between failures. It's going to follow a Weibull distribution in hours, and the mean time to failure will follow a log normal with 1.5 in hours. So typically Weibull probability models are really good to represent the time between failures. That's the probability distribution that is commonly used for those purposes. For the mean time to failure, there's no specific probability distribution. This will vary, but for time between failures, that's the most common distribution that you will observe, the Weibull. So it has a shape that matches that behavior quite well. One thing that I want to discuss today as part of this lab is the use of the warm-up period. Does anybody knows what this means? What is a warm-up period and what is the uses for it?
Don't you use it to reach like a steady state distribution? So you like run through to get to like a steady probability rate?
Yes, so you were saying, I'm sorry, thank you, Alex. So the idea, let me use my pen here. Yes, so it connects with the steady state, as Alex was saying. So let's call this time 0, and this call this performance measure. So that could be something like cycle time. For example, we can be looking at the cycle time, but it could be any performance measure. In this case, we're going to look at cycle time. Okay, so say we're looking at 10 days. So let's say we are concerned about the cycle time, and we want to make sure that we collect the right information to make some insights or to get some insights from the system. So what happened when you start, for example, let's think about a manufacturing process, and the machine or the manufacturing line that you're going to be using, and you're going to start processing right now. Let's call it that time 0. What will be the status of the machines in that manufacturing line when you start the processing? Those machines are going to be empty, right? So you will expect that that first part that goes through the machine goes through the process really fast, because there's no queues there, right? You will go straight through the system. Second part might find some queue depending on the processing times of the machines, but it will wait only for one part to move forward. Third part might get a longer queue, fourth part, so on. So at some point, you will see that your system will be busy, or your machines are going to be busy, or your bottleneck is going to be busy, and you will see some queues happening in the process. So if we look at the performance of your system based on cycle time, you will see that at time 0, the cycle times could be low. And as you add more entities into the system, that cycle time will be growing, because now you have more entities, you have queues forming. But at some point, long term, you will see that that performance measure will reach steady state. It will not go farther than that point. I mean, you might see some variation, but it will be mostly constant. And that's what we call reaching steady state. Because you know that at that point, queues are formed, and queues are not going to grow more than that. So typically you will see more or less the same cycle time of the parts. So what happened with the probabilities and then the analysis that we are trying to do is that if we take into account this part of the process, those statistics can be misleading, right? Because those are going to pull the numbers down. Remember, you started with an empty system. Cycle times are very low. So if you take into account those observations, most likely your statistics are going to be looking better than what you actually see in steady state. So what we do with the warm-up period in simulation is to find this line. I'm giving you that number, calling that 2 hours, which is basically what's going to do is not going to take into account these observations, and it would only account for the rest of the, I'm sorry, this is 2 days. This is the warm-up period. So it's not going to take into account these numbers. It's going to compute the statistics only looking at these 8 days where the system is in steady state. So those are the insights that you're looking for. You don't worry about, because most likely, again, if you add that part of the information, your performance is going to look better than what it actually is. So, for example, if you are in your projects, I remember one of you mentioned that you got there, and when you got there, there was no line, and then suddenly after 10 minutes, you started seeing this huge line, right? Your warm-up period could be that part of the hour in which you observe that empty system, right? Because you know there were no queues. If you take into account those numbers, your analysis could be misleading. I'm not saying this is part of your computing your input parameters. I'm saying it's part of the analysis. So you know those maybe 10 minutes before when you got started your simulation, those shouldn't be part of the statistic analysis, because you know at in those 10 minutes the system was empty, and that's not the behavior of the system at steady state. Okay. No, because the analysis will be based on assuming that you have reached the steady state. After that, it doesn't really matter. Like you're observing for a certain amount of time, right? Let's say 1 hour. So that hour you observe, the analysis was mostly steady state. Like you see the queues form, queues about the same size. So that's the part of the analysis that you want to focus on. Once the arrivals goes down, that means that the behaviors have changed for the system. So you're no longer looking at the peak hours, for example, in your system. Any other question? Okay, so I wanted to explain this because today we're going to be using that warm-up period. Part of the analysis. Okay, so let's look at the implementation of this in Arena. So remember, we're going to start with our model, previous model from last week, in which we have these 2 machines following a schedule. Okay, so if you go to the schedule, we had 2 schedules, one for machine 1. It was one for 18, 0 for 1, and 1 for 29. And this was for half hours. And then we had 1, 8, 0, 8, and 1, 8 for machine number 2.
Dr. Perez, I don't think we can see your screen on Zoom.
Oh, okay. So sorry about that. Were you able? Oh, yes, because I stopped. Should see it now, right? Can you see it now?
Okay. Yes, I do. Yeah.
Good. Okay, so we have 2 machines. Again, we are representing the same system that we covered last time. So in that one, we had 2 schedules, and those are the ones that I'm showing here. Schedule 1 for half hours, and schedule to 4 hours. And the capacity of those resources, if I go to resource here, were based on schedule, in which we were using machine 1 schedule for machine 1 and machine 2 schedule for machine 2. Okay, so something that you will notice in this module is that you have a failure column. And right now it says 2 rows. Take this out. So you see that you have here an area to code your failures. But before we get into that, we had to actually specify the values for the failures. So you can go to advanced process. If you go to advanced process, you can see this module right here that is used for specifying failures. So if we do double click here, we can name this whatever you want. So machine failure. So I'll call it machine failure. And then you have to specify the type of failure mode that you're going to use. In this case, we are going to use a probability distribution that is based on inter-arrival times of these failures. So we're going to change that to time. And then we're going to specify the uptime and the downtime for this system. Excuse me. So the uptime is the time between failures. Okay, so this is the Weibull 32.5. So see, we have the Weibull 30. See 2.5. Sorry. And this is in hours. So, and the downtime will be the time to repair. Follows a log normal 1.5. So the mean is 1, standard deviation is 0.5. It's also in hours. And then we can specify, we are not going to do it for this lab, but if you want to only to account for the time in which the machine is busy, you can type here busy and it will take that into account. If you want to know the different states that are available for your resource, like if you go to animate, let me show you something. If you go to resource here, these are the 4 states that are defined by ARENA. You have idle, you have busy, inactive, and fail. So if you only want to take into account busy, you can type busy. If you want, yeah, typically that's what you're gonna do. whether you take the overall time, including everything, or you take only the busy time where the machine is being used. Okay, so for now, you're just gonna keep it like that. And then the next thing we're gonna do is to go into the basic process. Now that we have this defined, and find the resource. I don't know why this is looking weird. Schedule. Yeah, okay, good. So we're going to include this failure here. And then this rule is going to be based on this. Okay, so if you're going to ignore, wait, or preempt. So typically, if you have a failure, you're looking at the third case right here. The resource requires maintenance immediately and requires a specified downtime. So the machine will suddenly stop and it will wait for maintenance to occur. So the preempt unless specified differently. And we're going to do the same thing for this one. So both of the machines will have the same failure mode. And check our model so far. So the last piece will be to incorporate the warm-up period. Oh, well, wait, there's something else we have to do. Time between failures, the mean number of parts per day. So in today's assignment, you needed to compute the amount of money or the daily revenue. And you were also running this for 10 replications. So the logic that you needed to implement require a separate logic for collecting that data. Today we're going to do, so in our previous lab, we were tracking the working process. Today we're tracking something else. Said the mean number of parts per day. How many parts on average are being processed by these systems? So typically, when you only had a 8-hour shift or 8-hour replication, you can just use the counter, count, you get the information you need. But here, we have a replication for 10 days. And we want to collect we want to know what the average number of parts being completed every day. So that means that even though the replication is 10 days, we have to collect 10 data points from each replication in order to get the information that we need. So how are we going to do that? Well, first, parts per day. I'm going to define a new variable here. And I'm going to call this parts completed. And this is going to be equal to parts completed plus 1. So instead of counting, I'm going to have a variable do the work. I'm going to be doing the work of a counter. You'll see why we need a variable in a minute. Okay, so we have parts completed plus 1. So every time a part is crossing this assign block, we're going to increase that variable by 1. Doesn't matter where it comes from. Every time it crosses this block, you will get a plus 1. And now I'm going to have a separate logic here. Create block. This create block is going to generate an entity every 24 hours, starting at time 0. Oh, well, we don't need to start at time 0, right? Because that'll be 0. So our first creation is going to happen after 24 hours. Yeah, that's true. So we don't need this, right? What do you mean? Yeah, we don't need it. That's right. So we are going to generate an entity after 24 hours. And the first creation is going to happen but I think like if we, you're right, we don't have to specify this because the system is going to wait 24 hours to bring the new entity into the system. But if we put the first creation equal to 24 hours, it will be doing the same. I think it's not going to change. So we don't have to do it. That's what I'm saying, because the model itself will take care of it. So go here, nice. Then I want to use a record block to get the number that I need after 24 hours. So this is going to be an expression. And I'm going to call the variable and I'm going to call this tally. What was the name we're using? Number of parts per day. So I'm going to call this parts per day. Okay, so after 24 hours, I'm going to call this variable. I'm going to save that number into this tally. So remember that the tallies work as a bag. So you get a data point and you put that observation into a bag. So if you get 10 observations, you put those 10 observations into this bag. And then at the end of the simulation, you want to know, for example, the average of all the observations in that bag. You can call the tally and do that. Okay, so our bag is going to be called tally, name parts per day. And then next, we have to make sure that we initiate that variable. We have to reinitiate that variable to 0. We want that after 24 hours, we want that. And after we collect that information that we need. We want that to go back to 0 to start counting on the next day. So you follow the logic, right? You go through the day, 24 hours have passed, you get the value of the variable, you store that value, and then you make that variable equal to 0. So you can start again counting after the second day have been completed. You call the value, you store that value, and then you make it 0 again. And then you continue that process until all days have been completed. And then finally, we have to do dispose. And save your model and check no errors. Okay, so last thing will be the statistics. Let me know if you have errors. Okay, so we have to add another output. Have to go here, it's called parts per day. So this is a tally. So I'm gonna compute the average of that tally. Parts, I'm sorry, parts per day. So this is confusing. So this here is average number of parts in the system. So this is the web, average number of parts in system, and then average number of parts completed per day is the second. Okay, so let's try to run this. Oh, well, first, we're gonna check our reports. Everything is good. Project parameters, replication parameters, 10 days. Okay, so what I'm going to do now, just to see whether or not there's difference in our numbers with or without the warm-up period. So I'm gonna run this without the warm-up period and see what the numbers I get. Okay, so I'm getting 263.24, average number of parts in the system, 12.83. So now I'm going to that's okay, it's close. So now I want to run this with the warm-up period, 2 days. So what you should expect? See the difference? at least for the number of parts completed per day. So working process, not changing much, but the number of parts completed per day is different. So this could be because, again, we start our system empty. So we might, at the beginning of the day, we might have some idle time in our machines, not too many parts being processed. But then as we get to steady state, we got all these queues, right? So we've been processing at a constant rate without any idle times. Any questions? So if there's no questions, you have a new assignment. Based on today's discussion, you can get started with that. And let me know if you have questions. You send me an email. Yeah. Any questions? If not, then I'll see you on Wednesday.
All right, thank you, Professor.
Thank you. Bye-bye.